Hi everyone, welcome to the final video in our crash course, Introduction to R for Reproducibility and Rehabilitation Research, or ReproRehab. In today's video, we're going to be working with the EEG data set that we've worked in the past, but we're going to do things a little bit differently this time. In the previous video, you've seen my script from the very beginning, and you have that kind of clean script file in your GitHub repository. In today's video, I'm actually going to live code this from beginning to end. So not only will you be seeing a bit more information about, how to actually go about doing some of the analyses for the data that we've cleaned, but you'll also be seeing a little bit more about the process of doing code from scratch. So in the GitHub repository, there will be like a completed clean version of this data file. But we wanted this video to be a little bit of a peek behind the curtain, as it were, so you can really see that I'm making mistakes, I'm stopping, I'm searching, for answers to questions, I'm looking at the help documentation for different functions, and I'll probably have to troubleshoot a couple things along the way. So this video might be a little bit slower than some of our previous videos, but hopefully that is actually a bit illuminating. All right, so first let's come to RStudio, right, as our design environment, and I've just got a blank script file here. So one of the first things that I'm going to do is give this script file a title. So I'll make a comment, and I'm just going to call this, statistical analysis of EEG data, parentheses, example. And then the author is me, and the date today, although this will obviously make the video harder to use in the future, the date today is October 26th, so I'll say 22-10-26, because according to the International Standards Office, this is actually the best way to write a date. Do the year, then the month, then the day, and that's ISO compliant for writing your dates. Okay, once I have that information in, what I'm actually going to do is go ahead and save this script file in the folder where I'll want to use it. So in this case, I'm going to my documents folder, then to GitHub, and then inside of GitHub, I'm going to my ReproRehab folder. So you might have cloned this repository to a different location on your own device, but I'm going to go ahead and save this file inside of the scripts folder. And you can see here's all the scripts we've worked with previously. I'm going to make a new name for this. I'm going to call this script 04. Let's call this data analysis, and I'll save it in that scripts folder. So one of the first things we'll want to do inside of any script file is to set our working directory. So before I set it though, let's just say get WD to see what the working directory is. And you can see down here in the console window, it says it's the documents folder. If I really wanted to figure out exactly where this is located, I could try to add things on to this address manually. A simple shortcut though is that I could go to session inside of RStudio, set working directory, and then set to source file location. And that's going to set the working directory to the place that my script file is currently saved. So this could be helpful as a shortcut, but as we'll see, it's going to create one problem for us. So if you're working inside of RStudio, this is a good shortcut, but it sets it to the scripts subfolder. Right, and I might not actually want to use the script subfolder as an example, because again, if I come back to Windows Explorer, GitHub, ReproRehab, I actually just want to set the ReproRehab folder probably as my current directory, because then that's going to make it easy to go into, for instance, the data folder and get the data that I need. So this is good. It's gotten us a lot of the way there, but it's actually taken us a little bit too far, and we don't want to be in the scripts folder. As a convenient shortcut though, I can take that address, come back up here, and now I'll just take scripts off the end. And now if I say set working directory and then get working directory, now you can see it's actually just set to the ReproRehab folder. And if I wanted to just make sure that everything I need is inside of that folder, I could say list.files. And there you go. You can see there's the README, there's the data folder, and there's the scripts subfolder. So let me go ahead and save that. It's good to save early and save often as you make these different changes. And then the next thing I'll probably want to do once I have my working directory set is to load some libraries that I think are going to be helpful. So almost always when I'm working on a project, I like to have the tidyverse library loaded. So let's go ahead and do tidyverse. Let's go ahead and do the companion for applied regression. And let's go ahead and do the easy package. And add that library because easy is for factorial analysis of variance, which we might want to do with some of the EEG data that we're working with today. So let me go ahead and load those libraries. Oh, you can see we get some masking warnings. So like the recode has been masked from dplyr. The sum function has been masked from per. Not too worried about that. Because if I ever actually need to use dplyr's recode, I can always call it with dplyr : recode, and that will give me the dplyr specific version of that function. But let's move on to the next thing. So I set my working directory. I've opened the libraries. I think I might end up needing a few more. Hopefully not. But that's the fun of live coding. So let's see what we want to do next. All right. Let me do list.files again. And then I'm going to look inside of the data subfolder. Oh, whoops, and this needs to be in quotes. And you can see we have the EEG subject files, which we aggregated together in a previous video to create the master EEG data set, which we had then cleaned to create data_processed_EEG. So that's the one I'm actually going to want to import for this session. So let's say data is read.csv. And then I need to tell it what I want to import. And remember, again, this is in the data subfolder, and my working directory is currently just set to the ReproRehab folder. So I'm using the dot to say, okay, take the current working directory, then go into the data subfolder, then go into data_process.csv. That's what we want to import. There are a couple of arguments that I know we will want. We'll want to say header equals true, because there is a header in that CSV file. We can also say strings as factors equals true, because there are some string variables that we'll want to automatically treat as a factor. Let me go ahead and do that. Looks like we successfully imported the data, so that's good. We've got 2,600 observations with 13 variables. If we wanted to take a look at just the first few rows to make sure it imported correctly, we could say head data. You can see it's got this like index variable, our subject ID number, the condition, whether it was eyes open or eyes closed, the hertz, and again, remember that these are the power spectra for these different conditions. So we're looking at the power in the signal at each frequency. So these are in approximately 1 hertz bins, right? Just counting up. And then across different regions, we have the power in the signal at 0.99 hertz, 1.99 hertz, and so on. And we, in previous videos, had calculated averages for the frontal, central, parietal, and occipital regions. We also calculated log transformed versions of the same variables because we as we saw, power tends to be pretty positively skewed. So putting it on the log scale can make it a little bit easier to work with. So now, what do I actually want to do today with respect to statistical analysis? Well, I think it would be helpful to look at the whole scalp. So we're going to look at all of our different regions, but we're probably not going to look at all of our different frequencies. So what we're actually going to want to focus on is the alpha band, which is a region between 8 to 12 hertz. And we want to look at the alpha band because alpha power is essentially the brain's idling frequency. When an area of cortex isn't receiving a lot of input, or when it's basically when it's at rest, you tend to see an increase in alpha power. So when we're going between eyes open and eyes closed conditions, we should see an increase in alpha power, especially in the occipital cortex, because that's where a lot of visual information is getting processed. So we'll want to look at alpha power across the whole scalp, but we're especially interested in alpha power in the occipital cortex and the difference between the eyes opened and eyes closed conditions. So first, maybe just to get a sense of how we might want to use that, let's actually open up a previous script file, which is something I do a lot when I'm coding, because if I know that there's something I kind of want in there, then I can go and copy it, and that can save me some time. So let's go ahead and open a file. In fact, we're going to open our previous file in which we were doing data visualization. So this is script 03, which if you're watching this video, hopefully you've worked with before. But if we come down to a lower place in the script file, I don't remember exactly where. We made spaghetti plots, we plotted the differences between eyes open and eyes closed conditions. Okay, let's start with this, just to take this GG plot code. Okay, so I'm going to insert a comment here. So I'm going to say example plot illustrating alpha difference. And what I'd like to do is plot alpha power in the eyes open and eyes closed conditions. And I'm going to try to highlight the alpha band for you in a figure so that it'll be a little easier for you to see exactly what we want. At the moment, though, we've got a little bit of a problem because I've got all the data for the individual subjects, and I don't think that's actually what I want to plot right now. I just want to plot the individual condition averages. And get those condition means. So I'm first going to actually do some reshaping of my data. So I'm going to create a new object which I'll call data underscore cond underscore av, so that these are the condition averages. I'm going to take the original data, push it through a pipe into the select function, and then I'm going to select the columns that I want. So I want hertz, I want occipital power. Oh, whoops, I also want condition. So I'll take condition, hertz, occipital, and I think I mostly want to plot this in raw space rather than the log transform space, at least as a starting point. But you know what, let's go ahead and take all of our regions, just in case I do want to do something different with those different regions. Okay, and then I'm gonna first push the data through the select function to take only those columns, and then I will say group by, and I'm gonna group by condition. So what this is gonna allow me to do is average across rows within a condition. That's right, so I'm ignoring what subject you are. I just want to get the mean in each condition. And I will also do that by hertz, because I want to, for the for this condition at 1 hertz, average across all subjects. For this condition at 2 hertz, average across all subjects. So I'm going to group by condition and then by hertz, and then I will say summarize, and I'm going to want to create a summary for each of my different brain regions. So let me go ahead and just kind of put them in the summarize function for now. And I will create a new variable, which I'll call, you know what, it's not an elegant variable name, but I'll call it frontal average, and it's going to be equal to the mean of the original frontal variable. And just in case, I'll say na.rm equals true, just in case there are any missing values in these data. I'll do the same thing for the central region. I'll create a new variable called central average, which will be the mean of the original central column. na.rm equals true. And so on for parietal. And for occipital. And calling, I mean, I wouldn't have to call this average here. You know, I could call this like frontal, but then it might get confusing that I have this aggregate variable and also another variable named frontal. So you could do it either way, because I don't necessarily trust myself to keep track of my variable names, especially when I'm live coding like this. I'm going to be very explicit that this is an average and that this is an average, and then that these are all my original variables. Oh, and RStudio is nicely notifying me, you know, that I have a expected comma after the expression, but I have an unmatched opening bracket, right? So I have na.rm equals true. That's fine, but what I need is another closing bracket to actually end the summarize function. If I run all of that, I should get a much shorter data set, which is the data condition average, which is 6 observations of 6 variables, which if we look at that data, you can see it's got the eyes closed condition. It's got all my hertz down to 30, which we had previously filtered out. And then for my eyes open condition, all my hertz down to 30. So one thing that we might want to do, just because, again, of this extreme skew in the data, is I'm actually going to remove these first 2 rows as well. So I'm not really interested in anything below 2 hertz anyway, and just because it's going to make my graph a little bit easier to read. For my final data set, what I'm going to say is filter, and I'm going to say filter greater than 2 for the hertz variable. And now if I do that, you can see over here, I've lost 4 rows. So it looks like it's done what I want it to do. And if I click on it, you can see now my first observation is actually at basically 3 hertz, 2.991. And I've dropped off those very low frequency, high power parts of the power spectrum. So now when I actually go to graph this, hopefully it'll be a little bit easier to see. All right, so let's go out to our data here. For my graph, what I'm actually going to say is data underscore cond average. And then for my x-axis, I want this to be hertz. But rather than difference in ln power, I want this to actually be my new variable occipital average. Okay, and then for the lines I want, I don't want this grouped by subject ID or colored by subject ID. I actually want this grouped by condition. And I can color them by condition as well. But actually, maybe rather than color, let's change this aesthetic to something like line type. I'll delete the alpha because I'm not worried about any transparency here right now. And then this is the downside of copying and pasting something, because now I have a bunch of stuff I don't actually want or care about. Let's just start with this. I'm going to get rid of the facet wrap function. I'm going to get rid of the geom line. And all we'll do is we'll say, okay, scale x continuous is frequency. Scale y continuous is power. That is correct. This labels argument, I don't actually need anymore either. Let's just see what this graph looks like, and then we can improve it from there. Uh-oh, object condition not found. Did I spell it wrong? I spelled it wrong. It's not DT, it's DIT for condition. There we go. So that looks pretty good for actually kind of highlighting what we want to look at. Again, these are the averages, right? So I'm missing the data for each subject to show you the average traces in each condition. Oh no, but I left my legend turned off, so I don't have any idea which condition is which. If you're familiar with EEG data and what I said about how alpha power works, you might be able to figure it out. But for the sake of clarity, let's change the legend position argument to the bottom. And now you can see, aha, the solid black line is the eyes closed condition. The dotted black line is the eyes open condition. And this might, on some ways, look like a pretty boring figure because it's just black and white, but it's simple, it's clean. I like it quite a bit. The one thing I might want to change is actually highlighting the frequency range that actually corresponds to alpha, because that's what we're going to be really interested in our analyses. Oh, and I forgot there's one other layer to this as well, actually, because we have older and younger adults in our study. we'll want to actually look at this as a function of whether or not you are a younger or older adult. Oh, and unfortunately, it doesn't look like I actually saved the data with a variable that tells me what group they're in. So I'll have to create a new variable called group here back in my original data that tells me whether or not someone is a younger or older adult, because it's in their subject ID, but it doesn't actually tell me I don't have a column that tells me what group this person belongs to. So let me actually back up a tick to before I have created aggregate data. And I want to create a new variable in my data frame where I'm just going to take the first two characters, right, whether it's OA or YA from the subject ID variable, and I'm going to save that as a new variable called group. Okay, and in order to do that, I think I want to use, I think it is called str_sub for string subsetting. Yes, so this is part of the stringer package, which is part of tidyverse. But the string subset will give us a subset of a particular string, and we can tell it where we want to start and where we want to stop. So before I actually make this variable, let me just try it out on my vector of subject IDs. I'll say start equals 1, end equals 2, and I think that will take the first two characters from the left-hand side of the string. Yes, it looks like it did that correctly. Remember, I just have this is just on that whole vector, so I've just got heaps of these things. Actually, I have 2,640 of them because that's the length of my data frame. But it looks like it's correctly pulling off the first two things, which is what I want. So I will keep the subject ID part in there because that's what I want to retain. But I am going to say data, and then I'm going to push that through a pipe, and I'm going to say mutate to create a new variable. And I want to call this variable group, and group will be the output of this substring argument. And if I do that, it looks like yes. So okay, here's my group variable. It's showing me this, only for my first two subjects because I printed this to the screen. But you can see that, okay, when I had, oh boy, this is hard to look at. There's so many rows. But yes, I've got, older adult 01, group is OA. So that seems to be working the way that I want. So what I'm going to do is actually overwrite my data set with this argument. Now you'll see that my data frame has 14 variables. Group is over here at the end, but that's okay. We've got a group value that we want, and we can double check this by saying summary data $group. Oh, whoops! So this is not what I was expecting. So this is length to 2,640, which is good, but class is character. So it's not actually treating all of those OAs as kind of levels of the same variable. It's treating the first time it sees an OA as a unique character, and the next time it sees an OA as a unique character. So if I actually want it to treat this variable as a factor rather than a character, I'm going to go back inside this mutate argument and just say when you take the output of that substring function, convert it to a factor and save that as the group variable. And now when I do it, you can see I've got 1,380 observations for the older adults and 1,260 observations that are younger adults. And that, seems reasonable because I should have about 60 observations per person. And I have, 20 plus older and younger adults in here. So allowing for some missing data, if I have, 60 times 20, I should have about 1,200 observations. And, I think it's actually a little more than 20 because I think there's 22 younger and older adults. I don't remember exactly. I probably should be better prepared. But let's change that to like times 22. Again, just ballpark. These seem reasonable, so I think it's working the way that we want, allowing for a certain amount of missing data. We should, of course, if you're actually doing this, for publication, go in and see, okay, exactly who is missing and does that match up with like a master log that you have. For now, though, it looks like we've got a factorial group variable in our data now, which is what we're going to want to use. So I'm going to come back down here and I'm going to rerun our data condition average, but I'm going to actually call this data group condition average. And I'm going to add our grouping variable in here to the group by argument. So it's still going to select those initial columns, but now it's going to group it by group. Are you an older adult or a younger adult? Then by condition, then by hertz, then do all of our averaging, and then filter out rows less than 2. It says error in vspace styles, attempt to apply a non-function. Uh-oh. Well, that's not good. Why is it unhappy with me here now? Oh, I think I know why this is causing a problem. I forgot to include group when I selected my variables. So I was telling it to group by a variable that I hadn't selected. Now it seems to be working. Okay, yes, summarize has output by group. Condition, you can override using the .groups argument. But I think this should be fine because let's look at our data now by group and condition. So I have older adults, eyes closed. If I go down to 30 hertz, that should switch over to older adults, eyes open. Looks good. I go down to 30 hertz. And it says younger adults, eyes closed. Yep. Down to 30 hertz. Younger adults, eyes open. And then I have the average power in each of those conditions. So, okay, that looks like what I want. So let me go ahead and close these other windows. It's getting a little busy in here. I'm going to go ahead and save where we're at. And now let's try this plot again. But what I'm going to do is I'm going to add a facet wrap by group. Oh, and let me add a plus at the end there. Oh, it's not happy about that either. Oh, sorry, because I didn't change the name of the data. See, this is the downside of like going back and not updating names for your things. Okay, so ggplot data group condition average, because I don't want just the condition average, I want the group condition averages. Aha, now we're cooking with gas. We've got our older adults on the left, our younger adults on the right, and nice power spectra showing the difference between the eyes closed conditions in black and the eyes open conditions as a dotted line. It looks like there is a pretty nice difference in the alpha band here if we look at our younger adults versus our older adults, where the younger adults seem to have greater modulation of the alpha power, whereas older adults seem to show less modulation of alpha power between those two conditions. So now, coming back to the thing I mentioned, maybe it was 30 minutes ago at this point, I actually want to draw a little gray box in here to show that I exactly what the alpha band is. Because I would really like to include this plot so that it's easy for readers to understand what my raw power spectra look like. So I'm going to open up a browser window. And I don't remember how to do this, so I'm just going to say ggplot. What do I want to say? Like shaded box? Add shaded region to ggplot. That seems like a good one. Hey, look, this link has been visited before, so this is probably something I've searched on before. Taking us to Stack Overflow, a lovely community where people help programmers understand and troubleshoot problems. And it looks like the geom rect is what I might want to use. So geom rect, which has aesthetics for the xmin, xmaximum, ymin, and ymaximum. Okay, so let me come back in here and we'll give that a try. The order does matter inside of ggplot, so I'm actually going to add this geom rectangle before I draw my lines. And I'll say AES, and then xmin equals. And so on the x-axis, the alpha band, I believe, goes from 0 to x max of 14 hertz. Anyone who's a big EEG processing person, feel free to yell at me in the comments. I believe it's 8 to 12 or 8 to 14. Actually, you know what? Let's just go back to our browser. I'll just say EEG frequency bands. Keep in mind, this is not how you would want to define this when you're actually probably doing something more robust. Okay, This resource at least seems to say it's 8 to 12, not 8 to 14. So let me change this to 8 to 12. But for our y minimum now, how far do we want it to go on the y-axis? I'm going to say negative infinity. And for y max, I'm going to say positive infinity, just so it kind of goes all the way. It'll exceed the dimensions of my graph. Hopefully saying infinity does not break it. Oh, hey, okay, so it added a shaded region that is a good bit darker than I probably want it to be. So let me change. It'll probably be fill is the argument. I'll say fill equals gray. I never remember the direction the numbers go. I want to say gray 20 will be like a lighter shade of gray. Nope, that's darker. Okay, let's call it gray 80. There we go. So now I've highlighted the alpha region. So this would be, close to a figure I might actually put in a paper where I'm trying to show, okay, here are my raw power spectra. What I ultimately want to analyze is the power in the alpha region. And the difference in that power between younger and older adults as a function of whether or not their eyes are open or closed. So let's go ahead and save this script. And then the next thing that I'm going to do is have to prune my data down to get just the average power in the alpha region for each person in each condition. So let's start with our data again, right? Head data. Actually, let me make a new comment here. And actually, I'm not sure if we've really talked about this as we've done this coding, but a really handy feature of RStudio is you can go in and add section headers. So I'm actually going to call this section 2. So I'll add a comment. I'll say 2 point, and you don't have to number it. I just like numbering it for numbers' sake. And I'm going to say something like calculating mean alpha. And then if I add 4 hyphens, you'll see this little heart symbol appears over here. And now I have a header that I can jump between here. So let me actually come back up here. Maybe I'll call this section 1, example plot illustrating alpha difference. Now that's a header. And now if I want to jump around in my script, I can actually just click on the different subheaders. So another great feature of using RStudio as a design environment in order to manage your workflow and make things a little bit easier on your memory. Okay, but now, what do I need to do? Well, I have this data set. It's 2,640 observations and 14 variables long. What I would really like to look at, though, are not all 1 hertz increments of the power spectrum for each person. I just want to look at the alpha band, and for the ease of this analysis, and this is very similar to what a lot of EEG papers would do, rightly or wrongly, but across the whole alpha band, I'm going to take the average for each person. So as you can see, I don't have a variable that tells me if it's in the alpha band or not. But what I can do is if I get creative, I can ask, if the hertz are within a certain limit, then it can be in the alpha band. So there would be a number of different ways you could do this, but let me just say, actually, before I make an if-else statement, let me just create an example string that might be helpful for seeing how this works. So I'm going to call this x. X is going to be a sequence from 1 to 20. And you can see, all right, here it pops up in my environment. X is the values 1 to 20. If I want to print X to the screen, there we go. It's those values. Now, so this will be a good way to test out if the little statement I want to write is working before we actually go and do it on all of our data. So let's just say if else, and then this will allow us to test if a certain thing is true. So let's say if X is less than 8, right? Because that's below the value that we want to start at for the alpha band. So if X is less than 8 and that evaluates to true, let's call that not alpha. And then if X is, if this evaluates to false, what do we want it to do? Well, if X is also less than 14, then we want that to say alpha. And if X then is greater than 14, we want that to say not alpha. Oh, shoot, and I said 14 again, and I mean 12. For some reason, 14 is in my mind as the upper limit of the alpha bandwidth. Okay, but let's just try this with a variable x. Error in if-else unused arguments. Oh, whoops, I closed that in the wrong place. I want to say if x is less than 12. There's that one. So now, basically, this whole if-else statement is what happens if this first one is false, right? Because if this evaluates to true, it'll do this. If this evaluates to false, it'll now go to this one. So then it will evaluate the second condition, that x also has to be less than 12. So if x is greater than 8, but less than 12, it's going to put alpha, and otherwise it'll put not alpha. Ooh, and that looks like it might have done it correctly. But let's actually we'll make this a new variable just to get, or sorry, I want to, well, we could bind these into a data frame to see them side by side, which would be easier, but it's actually, this is pretty easy because of the width of the screen, right? So it tells us for the first observation, it was not alpha, second observation, not alpha, all the way up to the 7th, right? And then the 8th observation, it starts saying alpha. So at 8 is alpha, 9 is alpha, 10 is alpha, 11 is alpha, 12 hertz is not alpha. So this, you know, when I have these discrete values, that's one thing. But if does, you know, it's a question of, is this inclusive of 12 or exclusive of 12? So if it's exactly 12, it's not getting included. So let me actually switch this to less than or equal to 12 here. And now we've got, okay, if it was 8, it's alpha, 9, it's alpha, 10, it's alpha, 11, it's alpha, 12, it's alpha, 13, it goes to being not alpha. So that seems to check out. So this looks like it will work for what we want to do in order to actually recode all of our data. So now we could do this if we wanted to say data $, and we could call this like bin, or let me call it like frequency underscore bin. I'll take this and I'll need to update. I don't want to say X anymore. I want to say data $hertz. Similarly over here. And actually one thing I might do to make this a little cleaner, I'm going to indent these so you can see which arguments belong with what. And I'm then going to change this to data $hertz. And let me say summary, data $frequency bin. Oh, whoops, I forgot to make it a factor again. So let me make this a factor. Okay, so then we've got 352 observations that are alpha, 2,288 observations that are not alpha. If we wanted to get more detailed about that, we could actually code the proper EEG bands that these go with, you know, and say, okay, well, if it's this, it's delta. If it's this, it's alpha. If it's this, it's beta, you know, and something it's gamma. And we could basically daisy chain a bunch of these if-else statements together in order to do that. For the purposes of this analysis, though, I'm only interested in alpha, so this is good enough for what I want to do. Let's just do a quick quality assurance, though, to make sure that this does seem to be correct. So let me just say data $frequency bin. And I'm gonna, let's see, will this data $hertz by data $frequency bin. Oh, I actually want to do this the other way. I want this to be Y and this to be X. Yes, okay, so you can see that for values that are coded as alpha, we have Hertz values, around 10. That's, 8 to 12. For everything that's not alpha, it extends beyond that. So it doesn't actually include these values, but this would just be a quick check to make sure it seems to be working correctly. Because if I had any observations that, for instance, had a frequency of 15 Hertz coded as alpha, that would be incorrect, and I would know that something had gotten off in my code somewhere. But this certainly seems to be working correctly because, around, it's centered on 8 to 10. We could change the limits maybe to make that a little more clear. But it looks like it is working correctly. It's grabbed everything between 8 to 12 Hertz and called it alpha. Anything smaller than that or bigger than that, it's lumping into the not alpha category. Maybe, though, just to be careful about this, let's say that this is below alpha and that this is above alpha. And we'll now make that our new variable. And now if I plot it, okay, now I don't have to worry about that kind of overlap in my box plots now, and my coding has gotten a little bit smarter, right? Okay, everything above alpha stops at 12, between 12 to 8, that's alpha, everything below that is below alpha. So great. Okay, let me go ahead and save that. We're getting there. We've got coded as alpha versus not alpha. Next, we want to actually aggregate across the data in order to get the alpha values for each person. So in order to do that, I'm going to want to take my original data. I'm going to want to push it through a pipe. I'm actually going to go grab basically the same select argument as before, because I'll take all these channels. And then what I'm going to do is I am going to, well, could I filter? I don't think I'll filter the data at this point because I might be interested in those powers above and below alpha just for reference. So maybe what I'll do now is not actually filter them out. I'm just going to group it by that variable. And then I'll know, is it below alpha, is it alpha, or is it above alpha? And then in the next step, when we're getting to my analysis, that's when I'll actually filter those data out in order to do that. Okay, so let me say group by, what's I call this? Frequency bin, frequency underscore bin. And then I think that's all no, I need to group it by group and then frequency bin and then condition probably makes the most sense. So then it will tell me, are they an older adult or not? No. Oh, sorry, at this level, I need to group it by subject ID. Actually, you know what? Let me bring the head of my data frame back. I need to group it by subject ID because I need to do this calculation within each subject. And then within each person, I want to get the frequency bin. So that also means I'm going to need to add these variables to my select function here. I'll group it by subject ID, then frequency bin. So in each person, it will, within each bin, I also want to do condition because I want it in the eyes open and eyes closed conditions separately. So for, subject 1, eyes open, all the different frequency bins. Then subject 1, eyes closed, all the different frequency bins. Then it'll keep moving throughout my different subjects and conditions to give me what I want, I think. So let's then say summarize. And again, I will want the frontal through occipital electrodes. And now, because it's going to group by frequency bin, it's going to apply this calculation to all the values that are above alpha, all the values at alpha, and all the values below alpha. So what I can just do is I could say something like frontal underscore alpha equals mean Oh, actually, no, I shouldn't call that frontal alpha, though. That's not a really good tidy data naming convention because it's still just power. And then I'll have power above alpha, power at alpha, and power below alpha represented by a separate variable. So I'm going to be a little bit lazy and just call this frontal. And then I'll have central equals mean of the central column Similarly, parietal equals the mean of the parietal column. And again, just adding na.rm equals true in there, because if it hits any missing values, I don't want it to say that the mean is not calculable. I just want it to ignore those missing values. Okay. So I think this will give me what I want, but let's just, before we save it as any kind of data frame, let's just print the data to the screen to see if it looks right. Okay, so I'm getting my subject ID in a condition, the frequency bin above alpha, at alpha, and below alpha, and then it's giving me the calculation of the power at each point. So that looks right, and then I've got subject 1, eyes open, subject 2, eyes closed. So this looks right. It looks like I'm getting 3 observations for each subject in each condition at each of the different electrodes. It's telling me the average power. The one thing I forgot here, though, is that I do want to keep a group in here as a variable. So I can keep group in here with the summarize function. I could either group by group, but that's a little bit redundant because the subjects are all in different groups. So, you know, since I'm already grouping by subject ID, you could just put group in the group by argument, and that would work. To be a little bit more explicit, though, I'm actually going to put group in the summarize argument, and then just say take the first value of group for that subject in that condition. And so what that will do then, right, is when it looks at subject 1, all the values of group for subject 1 are older adult. So it's just going to say OA, and that should get repeated. And you can see that here now when I push that through, right? So subject 1, eyes closed, above alpha, they're in the older adult group. And then here's the average above alpha power for that person in the eyes closed condition. Here's the average alpha power for that person in those conditions. So let me go ahead, and I'm going to call this data underscore alpha power. Go ahead then and save that, and you can see now up in my environment I've got data underscore alpha power, 264 observations of 8 variables. And now I think we actually have the data in the format we would want in order to do our statistical analysis. However, what we might want to do is actually filter out the above alpha and below alpha rows. So let's maybe change some of our naming here to make that a little more clear. We could say data underscore, I'll just call this power underscore bind, because just in case, if I ever do want to come back to this, you know, maybe I want the above alpha power, maybe I do want the below alpha power, I might want this kind of temporary step to be saved. And then for the bind power, what I'll do is I'll pass that through the filter function, and I'll say that frequency bin has to be equal to alpha. And then if I do that, you can see it's going to select only those situations where the frequency bin is the alpha bin. And now I only have 2 observations for each subject in each condition, which is what we want. I've got alpha power for subject 1, eyes closed and eyes open. Subject 2, eyes closed and eyes open. Subject 3, eyes closed and eyes open. So that's what we would want. So let's actually save that output as data underscore alpha power. And that's going to, you know, cut it down now to only 88 observations because I've got 2 observations per person. But that looks good, and I think this is what we're actually going to want to use for our statistical analysis. So let's actually go to create a new header, and we'll call this section 3, and we'll call this a let's do a mixed factorial ANOVA of alpha power. All right. So what we'll want to do, let me actually bring back Firefox here. Let's look at easy ANOVA R. It looks like I've Googled this before as well. Let's look at the R documentation for performing an easy ANOVA. Okay, so Here's all the different arguments that we can specify within this function. I'm just going to go ahead and copy and paste this into R, and then we can fill in what we need in order to actually do our analysis of occipital power. Okay, so this is interesting. This gets into a bit of a stylistic convention for different people. When your code goes to the compiler, it doesn't actually care where the commas separating the different arguments are. So some people, like myself, tend to put commas at the ends of lines. But one downside there is it can be actually pretty easy to miss a comma. Which, if you've got a design environment like RStudio, isn't so bad because it will often prompt you and say like, hey, I think there's a comma missing here. So then you can kind of go back and fix it and add that in. If you're not writing things in a design environment or your design environment doesn't have that feature, actually starting lines with a comma rather than ending lines in a comma can make that comma more visible. And so this isn't necessarily like good or bad practice, I would say, but it does have the advantage of making these commas much more visible, so you're less likely to leave them out when you're trying to actually do your analysis. But easy ANOVA is the function that we're going to want to run, and you can see it takes the following arguments. If we have more questions about exactly what those arguments are, it's going to be explained to us in here inside of the help documentation. So let me come back over here, and for what we want to analyze, we want to look at occipital alpha power as a function of your condition, right? Whether your eyes were open or your eyes were closed, and your age group. So we're going to use this alpha power data. So data is equal to alpha power. Our dependent variable in this case is specifically occipital power. The WID, right, if we look over here in the help documentation, that's the name of the column in the data that contains the variable specifying the case or subject identifier. So in our case, that's subject ID, lowercase sub capital ID. Then we can specify within subject variables names of columns in the data that contain predictor variables that are manipulated or observed within subjects. If any single value may be specified by name of alone, if multiple values must be specified as a dot parentheses list. So in our case, we just have a single within subject variable, which is condition. So I'll replace that with condition. And similarly, we have a single between subjects variable, which is group. And then some of these other things don't actually apply. I'm going to go ahead and delete them. You could look through the help documentation on your own if you're really interested in that. We have a type argument, which we might want to consider. A numeric value, either 1, 2, or 3, specifying the sum of squared errors to employ when the data are unbalanced. So type 2 is the default because it will yield identical ANOVA results as type 1 when the data are balanced. But type 2 will additionally yield various assumption tests where appropriate. When the data are unbalanced, users are warned they should give special consideration to the value of type. Type 3 will emulate the approach taken by popular statistics packages like SAS and SPSS, but users are warned that that approach is not without criticism, which is fair. And this video is not about types of sums of squared errors, although if you haven't watched it, you should go check out my own video on types of sums of squared errors to help understand the differences between those things. I am going to change this to type 3, not because I think, if SAS and SPSS do it, we should do it just to be cool, right? But because I think that the exclusion of all the shared variants in parallel would be appropriate. And I think although we have some missing data in this data set, we have a more or less balanced design. So I don't think there's going to be any really strong collinearity between the effects of group and condition. So I think probably you could kind of set this to lots of different values for the type argument here. But I'm going to set this to 3 for our purposes. Okay, white.adjust only affects behavior if the design contains between subjects predictor variables. If not false, the value is passed as the white adjust argument to ANOVA, which provides heteroscedasticity correction. Okay, so this is an adjustment for violations of heteroscedasticity. The default is false, so I will leave that as false. So get rid of that. Detailed, the default is false, but you can see this is a logical argument. If true, it returns extra information, such as the sum of squared errors column, the intercept row, etc. in the ANOVA table. I like to see all of that, so I'm going to go ahead and turn that to true. And then return AOV. The default is set to false, but if true, computes and returns an AOV object corresponding to the requested ANOVA, which can be useful for computing post hoc contrasts. So I'm okay with leaving that false, but again, as the default, I don't actually have to have it in there if I want to leave it as false. So I think I've set this ANOVA up the way that I want it, so let's go ahead and run it. It does say data are unbalanced. Make sure you specify a value, well-considered value for the type argument. Error, data, one or more cells is missing data. Try using easy design to check your data. Okay, so we're going to have to take a look at our averaged data set to understand why that is. Because one of the conditions of the easy ANOVA is that you can't actually have missing observations, or it's going to go through list-wise deletion. By which I mean, like, if subject is missing a value even in one condition, then all of that subject's data need to be excluded. So let's just look in our occipital column. Well, I didn't see any NAs. Let me just do... Oh, whoops. Actually, let me do this under this header. Okay, so that's not the problem. It's not NAs there, which probably means that someone is missing, like, conditions. But I'm not sure which one they are missing. So let me say condition plus sub ID. I think data equals... Oh, no, is that... Okay, maybe this isn't how I need to do this. All right, let me try one more thing. Because I think I can use the table function, which would give me kind of a handy summary. But maybe I need to say... give it each of those vectors. Nope, only applies to vectors. Is it xtabs? Ah, there we go. Okay, so xtabs, not table. That's what I want to do. And now you can see it's giving me a summary of each subject in each condition. And then now we can see who's missing data. So subject OA22 is missing the eyes closed condition, and subject OA24 is missing the eyes open condition. So because I have to have I can't have missing data within the within subject's ANOVA, or the mixed factorial ANOVA, I need to delete these individual subjects in order for that ANOVA to run correctly. So what I'm going to need to do is actually filter out those subjects. So I'm going to truncate this to just call it alpha. And I'm a little comfortable calling it alpha, and I'll still know what it is, because as a convention, you might have noticed I'm naming my data sets in all caps. So anything in all caps, I'm trying to remember is a data frame. So if I just call this alpha for the sake of conciseness, I can pass data underscore alpha power through a pipe, and I will filter out sub ID does not equal OA 22 or sub ID does not equal OA 24. Because then if it doesn't, I'll keep it if it doesn't equal that, and I'll keep it if it doesn't equal that. And actually, before I save this to a new data frame, let me see if that's working correctly. Okay, it seems like it gave me a result that made sense. All right, so let me save alpha. And then let me do my crosstabs again. But now I'll refer to the alpha data frame, which has all that filtered out. Nope, that didn't work. Why is that not working? Oh, I think I need an and, not an or, because when it's evaluating this one, subject 24 is not 22, so it's getting kept. And subject 22 is not subject 24, so it's not getting kept. So let me try and. There we go. So now switching that from an or to an and, you can see data alpha power had 88 rows. Alpha has 86. So I've successfully screened out those two subjects who are missing conditions. Now if I do my crosstabs, yes, you can see that OA22 is still retained as a level because it's still represented as a level of subject ID, but you can see there are no data for that subject. OA24, there are no data for that subject. And actually, if I go to look at the data, let's just scroll down. You can see there aren't any rows for OA22 or OA24 because again, although we have those values saved as levels, that is a property of the factor variable. So it knows that subject ID is a factor and OA22 was one of the levels. So unless I re-level that factor, it's going to remember that and show me, hey, OA22, there are no values at that level. So that's actually a desirable feature, but I do want to double check and just make sure, hey, there aren't actually any rows there and they aren't just like, rows that say NA or something like that. So that's useful to kind of check both of those things. Now though, I should be able to run this easy ANOVA. Oh, whoops, still got an error. One or more cells is missing data. Maybe I do need to re-level it. Okay, let me just check one more thing here. If we say X tabs, actually I'll copy this. I'll say condition by group. Okay, that looks okay. Oh, I see. Whoops. I forgot when I filtered these out. So when I filtered out these two subjects to just create alpha, I did not update the name of the data frame inside of the easy ANOVA function. So let's say just data equals alpha. Run our ANOVA again. Aha, perfect. Now we actually get an ANOVA output. So we can see that we've got the intercept. Gives us the sum of squared errors explained by the intercept, the F value for that. Usually though, the intercept, right, is not an interesting test because that's just the grand mean. And we're really interested in how things improve the prediction of our model above and beyond the grand mean. So let's instead look at something like the group variable. Well, there was no main effect of group that was statistically significant. It was about 0.29. There was a statistically significant main effect of condition, so it looks like alpha power does actually change across conditions, and there was not a statistically significant group by condition interaction, although it's important to point out, of course, we weren't powered to detect one in this study, so we don't want to misinterpret this non-significant result as evidence of no difference. There is a difference, as we'll see when we calculate some of the descriptive stats. It's just a difference that failed to reach statistical significance, whereas the main effect of condition does seem to make sense. And actually we say, okay, well, we saw some pretty big differences between the eyes open and eyes closed conditions. So that would seem to check out given what we saw in the graphs before. So now if we actually wanted to, kind of map these results onto the numbers in our data, we might want some descriptive statistics and a plot to help us better understand these data. So first, let's actually create a plot. So I'm going to say plot of alpha power, and I'll call it occipital alpha power by group. And let me come back up and just steal some of my ggplot code. And now what I will do is I'm going to look at the data set we use for analysis, right, alpha. And what I'll have on the x-axis is condition. And on the y-axis, I'll have occipital power, because that's what we want to look at. And again, let's just peek at the head of our alpha data set to remind us what variables are what and what everything is called. I'm going to get rid of some of this stuff in the middle because I'm trying to think about how I really want to format this. Yes, I think I want condition on the x-axis. And I want occipital power on the y-axis because that was our dependent variable. But what I'm going to want is a geom underscore line. And let's say AES. Let's group this by a sub ID. And I'll say... You know what? Let's just start with this. Let's do subject ID. We'll say color equals. Let's make color a function of age group. So we'll say color equals group, and then let's do geom underscore point AES group equals sub ID, and let's say color equals group, and then I will say shape equals 16, which is basically just a solid colored circle in R. You can go online to see like lists of the different shapes and what corresponds to what, but I believe that's just a solid dot. And then let's say let's actually keep our facet wrap in there as a function of group. I'll have to change my x-axis now because this is actually condition. Power is still power, but I'm going to change this to alpha power because it's alpha power specifically. Oh, it doesn't like that. Discrete value applied to a continuous scale. Yes, because condition is a discrete variable, but I'm saying scale x continuous. So let me change this to scale x discrete. And there you go. We've got a plot that actually shows us the individual differences for each person, right? Whether you're an older adult or a younger adult. And it does look like there is some evidence of modulation here for the older adults versus the younger adults. One thing that we do see is, there is this positive skew. So we might actually want to analyze our data using a log transformation of the alpha power. So we could actually get into, kind of doing a statistical test for is it a violation with respect to the distribution of residuals. But for now, let's just consider this visually for a second and say, let's look at the log of occipital power. And I'm going to say log plus 1. So 0 remains 0, right? The 0 point remains the 0 point, but it's because if it's 0 plus 1, I take the natural log of that, it goes back to 0. But now what this will do then is transform the scale of all these other variables. Oh, whoops. It's not called ln in R. It is just called log. I'm getting Excel functions mixed up with R functions, which is terrible. So if I just say log, that will take the natural log. Okay, and now you can see on the log scale, you can actually see more of our data points. And now you can this might make it a little more clear why we didn't actually see that big of a difference in terms of the modulation between the age groups. Although we had some younger adults who had really substantial alpha power, especially in the eyes closed condition, there is a lot more overlap between these two age groups than we might have first thought. Interestingly, we have one older adult who actually shows greater alpha in the eyes open condition. Although there's a couple who show that trend, so there's a little that's a little bit surprising. But these data were pretty noisy, so maybe not all that surprising. But let's actually go back and do this same analysis. And again, I'm just doing this for illustrative purposes to rerun our data using the log of the occipital power. You should probably know either a priori going into your analysis whether you're going to log transform it or do like a formal test of the regression assumptions. But again, because that's not fully the purpose of this video, I'm kind of just eyeballing it from this figure to say, oh wow, there is some pretty substantial positive skew here. So therefore, I am going to log transform the data. So I'm not saying that this is best statistical practice. You shouldn't just run your data a bunch of different ways. But I'm just doing this for illustrative purposes. And I think in these data, occipital plus 1, because I said ln again. I gotta say log. Actually, it won't do that, interestingly. Okay, so I can't specify that inside of the EasyAnova function. So let me back out a second. We'll go to alpha. We'll create a new variable, which we call log. I like ln for natural log. It just makes it clear in my mind. So I'm going to say ln underscore occipital. And that's going to take the value of the log of alpha $occipital plus 1. And now I can actually change it in here to be the natural log. And now you could see, interestingly, we actually get a group by condition interaction. So good evidence as to why if you have a lot of researcher degrees of freedom, your false positive rate can increase. Because by analyzing the log transformed power, it looks like there is actually a group by condition interaction that I did not look at in the raw data. Probably the log transform is actually more appropriate. But I did not actually enter into these data necessarily with that plan in mind. Maybe I should have, but for the purposes of this exercise, I had already done the analysis one way. Now it's, what's the right way to do it? You should have a well thought out analysis plan before you actually jump into statistical analyses. But again, if we're just going based off of my eyeballing of the skew and presumed violation of some of the regression assumptions, I think the log transform is going to be more appropriate. And certainly from what I know of the EEG literature, I think people typically do actually log transform their data prior to analysis. So we should think of this probably as more of an oversight on my part when I'm log coding. And this is why you should always have a detailed analysis plan when you actually are analyzing your data. Okay, so that is interesting. That means that we do actually maybe have some evidence for a modulation of the alpha power as a function of age group, which is certainly how it kind of looked in our raw data before. But let's proceed then with this analysis. We've got our log transformed outcome variable, and we also have our raw variable. So maybe to accompany a plot like this, it's also going to be really helpful to get some kind of descriptive statistics that we could present in a table that will help give us a little bit more information. So there are, again, a lot of different ways you could do this, but we're going to start with the alpha data set because that was what went into our analysis. I'm going to push that through a pipe. And then I think we will want to do group by, and we'll group this by group, right, which is our younger adults versus our older adults. And we'll also group this by condition, which is our eyes open and eyes closed. And then I will say summarize. And then we can pull out different things that we might want. So let's, for instance, get the mean. So I'll call it average because mean is actually the name of the function. So let's say average is the mean of the occipital column. I could then also get maybe the, I'll call it STD is equal to the SD, because again, SD is the function for standard deviation. So that'll be the standard deviation of the occipital column. And then I could say count is equal to the length of the occipital column. And again, this is grouped by group and condition. So when I say length, it's not across all the data. It's within a particular condition for a certain group. How many observations are there? Oh, and let me put a comma there. And then let me actually, before we do that count, maybe let me do also an ln average and an ln standard deviation. And we'll do that for our log occipital power. And we'll have both of those. And maybe especially for the Let's also get a median. So I'll say med, because again, median is the name of the function. So let me say median occipital. And then we can do the same thing for the log transform data. And let's do that. Okay, now we've got a nice table here of descriptive statistics. So we've got our older adults in the first 2 rows and our younger adults in the next 2 rows, right? And you can see we've got 22 older adults measured in each condition, 21 younger adults measured in each condition. We can see the effects of our positive skew by actually looking at the discrepancy between the mean and the median. Because remember, the mean is very sensitive to outliers. So when I have these extreme positive values in the data set, it's going to pull the mean in the direction of those positive values. So especially in those eyes closed conditions, the average should be a lot higher than the median. And it looks like it is, especially for the younger adults, an average of about 9.59 and a median of about 6.28. For the older adults, it was a mean of about 5.50. A median of about 3.30. When I've done my log transformation, you can see that I've wiped out that skew because now the average and the median are basically in exactly the same place, indicating we have a symmetrical data set because the mean, as you might remember, puts an equal mass of scores above it as below it. The median puts an equal number of scores above it and below it. So if they're in the same place, that means our data set is balanced on either side because there's an equal mass in the bottom 50% and an equal mass in the top 50%. And that looks like our log transformation has really taken care of that positive skew. So again, probably should have thought about that before I actually started live coding any kind of statistical analysis and had a plan to commit to in order to in order to prevent taking multiple peeks at my data. But I can at least report both versions of the data nicely in a table something like this. All right, so I know that's a lot, but we've successfully written about 127 lines of code here. You've gotten to take a little bit of a peek behind the curtain to watch me mess up a number of times and hopefully fix it. I hope you've also learned some useful things along the way in terms of actually implementing some statistical analyses. Obviously, we didn't get into all the details of what you might do. If you have that statistically significant interaction, how would you handle doing post hoc tests in order to look at maybe the simple effective condition in the older adults and the younger adults. But again, those things are a little bit beyond the scope of this video. If you are really interested in those topics, feel free to talk to your TAs if you're part of the ReproRehab workshop. Otherwise, I also have other videos on my channel about like strategies for post hoc testing, and there's a lot of online resources for implementing post hoc testing in R. So I hope this has been really helpful for you, and I hope you feel a little bit more confident moving out onto your own to do some data analysis in R.